Here's the application question based on implicit differentiation. So we're given a function here in terms of the frequency of vibrations of a violin string. And we have three different variables that can affect that frequency. L is the length of the string, T is the tension, and P is the density. So we want to find two different things here. We're going to find the rate of change of the frequency with respect to the length. So for part A, we're going to hold T and P to be a constant. And then we're going to redo that and talk about the rate of change of frequency with respect to tension. So here, if we want to keep T and P as a constant, my suggestion on this would be to rewrite this equation in a way that allows you to see the variable and make it look more like a variable. Have that L written as a variable. So I'm going to have F equals, I'm going to say this is root T over 2 root P times L to the negative 1. So this whole thing here, this whole coefficient, that's all constant. It's big and it's messy, but it might as well just be a 7 because it's just a constant value. Now we're going to find the derivative of the frequency in terms of L. So I'm going to do df dl, which then would be this constant times negative L to the negative 2. So the derivative of the frequency in terms of the length would be negative root T over 2 root P, assuming those were constants, times L squared. So we can say that this is going to be, we see that the df dl, if we're looking, the last question kind of says what's the relationship between these, we would see that this square root is always positive, 2 root P will always be positive, and L squared will always be positive. So I see that this negative means that that whole thing, the whole derivative, df dl, will always be negative. So what this means is that the frequency is decreasing as the length increases. So here we have a relationship that the slope of the tangent is negative for the whole function, and that would mean that it's always decreasing. If we want to do the derivative in terms of tension, again, I would want to rewrite this and make that T look more like a variable. So I'm going to write this as F equals 1 over 2L root P, and that's my constant, times T to the exponent 1/2. So my constant value now is all of this stuff. And then I have a function of T, that T to the 1/2. So I'm going to do the derivative of this, the derivative of frequency with respect to tension is going to be this constant value times the derivative of T to the 1/2. So that's 1/2 T to the negative 1/2. So rewriting this, this would be 1 over, and I have a 2 there and a 2 there, so I've got 4 on the bottom, 4L, and then the square root of P and T. They're both on the bottom and they're both square roots. So here I see that the derivative of frequency in terms of tension is always positive. So we can assume that the length of a string is always positive, 1/4 positive, and a square root is always positive. So that will always be positive. So as tension increases, the frequency increases. So being able to analyze when a derivative is positive and when it's negative is valuable. It tells you about the relationship between two variables, and it's also important to recognize that you can often find the derivative of the same function if there's multiple variables happening in terms of different variables. So sometimes you might find the derivative in terms of the density or the tension or the length or whatever it is. There could be more than one variable changing, but it is possible to hold the other variables as constant and find out how the dependent variable would be changing in terms of just one of those.